Welcome back. In this video, we're going to talk about the differential formula for arc length. So we're going to deal with a function where its derivative is continuous on the closed interval. Using the fundamental theorem of calculus, we're going to take our arc length formula. This looks very similar. And we're going to define it a little bit differently. S is a function of x from a to some variable x. And then we're going to use that arc length formula, 1 plus f prime of t, the derivative of the function in terms of t, quantity squared, integrated with respect to t. So this continuous function measures the length of the curve on f of x from some point p sub 0, an initial point at a, to an ending point q at any variable x, as long as x is in that closed interval from a to b. S being the variable that represents arc length of a function for that. So we'll define that differential ds of dx, or the derivative of s with respect to x, is equal to essentially our integrand. This guy is the same as that integrand. And if you remember from trig, we used s as our variable for arc length. Okay, so this integrand we refer to as the change in arc length with respect to that variable x. So if I took that dx and multiplied that over here, I would have just the ds. I'm going to pull in another picture. So now what we can say is the differential of arc length. I took that dx and just multiplied it over here. This is how we define ds. And what we want to think of here, L, that arc length, is the integral of this differential ds, right? Because that's what we were doing. We'd be taking the integral of that. So we see these illustrations here. One is an exact interpretation of what we're doing, and when you think about that, that's exact interpretation here. That is a right triangle, right? We're just figuring out what that length is using Pythagorean theorem. And what we showed in the earlier video was that exact curve was exactly or very close to the secant. That exact arc length was similar to the secant arc length. And so we're using this exact formula here to kind of approximate this curve. And so we use those pictures to help us remember that ds equals the square root of dx quantity squared plus dy squared. So ds represents that change in s. And we can think about it a little bit differently. ds squared equals dx squared plus dy squared. That's just directly the Pythagorean theorem using this exact right triangle. And so what this formula really does is it lets us find kind of a general formula for arc length. All right, so not just a specific arc length over a closed interval, but some general, hey, this is the formula we would always use for arc length if we knew which interval values we were plugging in. So let's look at an example. And when we look at this example, this is really just about kind of understanding, how to manipulate these problems. So here we have a function, 4x squared minus y squared equals 64. And we want to show that ds squared equals 4 divided by y squared times the quantity 5x squared minus 16 times dx squared. So looking at this, the first thing we know is we need a derivative. We need d dx. So I'm going to go and take my derivative with respect to x. 4x squared minus y squared equals 64. I'm going to differentiate this guy. So this is implicit differentiation. I'm going to get 8x minus 2y dy dx equals 0. So I can manipulate this, move things around. I'm going to move the 8x over to the other side, which gives me negative 2y dy dx equals negative 8x. So at this point, I'm going to divide on both sides by negative 2. That gives me y dy dx equals 4x, and I can multiply by the dx. Y dy equals 4x dx. And the main purpose of this is just showing you that, we can manipulate all of these separate pieces. So let's look at what we have. We have up here that ds squared, and what we want to show is that ds squared equals this contraption, this group of values, numbers, variables, over on the left. And what you'll notice is we already have a dx squared in there. So thinking about what we know and what we defined on the other page, ds squared equals dx squared plus dy squared. I have ds squared. ds squared equals dx squared plus dy squared. If you notice, there's already a dx squared in there. So it looks like I might need to figure out a way to manipulate this so that I have a dy squared. So we're essentially proving I want to make this look like this, which means I'm going to turn my dx squared plus dy squared into that expression. All right, so in that case, I'm going to take this the dy and isolate it, divide by the y. So I've got dy equals 4x over y dx. So this right here is equal to dy. I can plug that in. So if I do that, I end up with dx squared, and dy squared will be 4x over y dx. And notice that needs to be, my dy value needs to be squared. So this is equal to dx squared plus 16x squared over y squared dx squared. Now, this expression we have, we're trying to make it look like what we started with, which was this. So, in order for us to do that, we've got to be a little bit creative with our manipulation. I'm going to factor out dx squared. And now it looks like this. So keep in mind what our goal is. We're trying to make this look like 4 over y squared, 5x squared minus 16. I already have that dx squared at the back now, right? See, I've got that right here. So this looks kind of similar, and this is where we just are learning practices of creative manipulation, in my opinion. So what I'm going to do is look at this. I'm going to try and add these together so that they're just one term. So 1 is essentially y squared over y squared. So I can write this as y squared plus 16x squared over y squared times dx squared. All right, now at this point we want to keep in mind something that we were given. We were given 4x squared minus y squared is 64. So I don't like this y squared that I have in the numerator. I'm okay with having the y squared in the denominator because I can factor that out, but I need to kind of get creative with this. So if we isolate this y squared, that's going to give us that x squared minus 64 equals y squared. I'm going to plug that in for my y squared in the numerator. So I'm going to go ahead and factor out the y squared in the denominator. And what that leaves me now with is 4x squared minus 64 plus 16x squared dx squared. So this, now I've got some like terms inside my parentheses. This is the same as 1 over y squared. The 4 and the 16, when I add those together, that gives me 20x squared minus 64 dx squared. And then you may notice, looking at both of the terms in the parentheses, we have a GCF of 4. I can factor out 4. That will leave me with a 5 and then also a 16. So I have 1 minus y squared. I'm factoring out a 4. That's going to go in my numerator, and that leaves me with 5x squared minus 16 dx squared. And so now what you'll notice is that we've formulated what we have down here at the bottom is exactly what's up on the top. And so what we've done is we've shown or proved that this is equal to that. All right, and so one thing you want to remember, especially about proofs, remember we start on one side and we manipulate it to make it look like the other. So you'll notice I only manipulated the one side, all right? So the main point of this problem, one, is to show you how we can deal with differentials, and then also to just kind of give you some creative manipulation techniques. So I hope that helps. And again, email me if you have any questions.